The work in progress track is always my favorite session of the workshop every single time. So without any further ado, please take it away. Please take it away, Adventium.
All right. What I'm going to be talking about is some work that we've been doing as part of Sergey's AIMEE program. Specifically, with the caveat that these are my descriptions, not necessarily his, what we're doing is coming up with a language that allows for representing the architecture and behavior of systems at a design level in such a way that you can rule in or rule out certain kinds of emergent execution defined as things you weren't expecting, not necessarily things that you actively stated that you'd prohibit. As far as the connection to this, the overall topic of LangSec, I can look at that in one of two ways. One is that both looking at emergent execution and looking at input validation, it's a question of somebody's going to be feeding you input, which you can view as a program or a programming language. And what you want to think about is what can they do to you with that, right? Have you ruled out invalid inputs in the one case, or in the case of emergent execution, are there corner cases in the way that your system operates that allows them to do things that are somewhat unexpected? As a way of achieving the goals that we've got in this workshop, in this program, what we've been doing is building a set of composable models based on an extended syntax for timed finite automata. I'm going to talk about, I'll show you examples, in fact, of the models we're building, talk about why. I'm going to say very little about the extensions for that automaton language. There's some in the paper. I'm happy to provide more, but not in 8 minutes. So the biggest thing that we're worrying about here is what's going on in the CPU microarchitecture. This is driven largely, but not entirely, by there being a slew of speculative execution exploits, but not just that. I mean, there's more recent work that, for example, some work by Evgeny Chuskin, Tom Benjamin, and others that looks at ways of building a machine that has a user-definable semantics, if you want, that you can build out of microarchitectural components, such that you can stay completely within valid ISA level instructions, but you have a machine whose semantics are almost entirely opaque. You can actually combine that with speculative execution to make it entirely opaque. What's here on this slide is just some examples of where this gets complicated. Okay, the Skylake architecture, none of what you see here, or let's say almost none of what you see here, is actually relevant to maintaining the invariants that provide the semantics for instructions at the ISA level. This is all about performance. This is all, how can I make things faster? Which means that there's an awful lot going on in this CPU that has nothing to do with that semantics. You can say, I have a valid set of inputs in terms of what that instruction stream is, but you have very little way of controlling, or in some cases determining what's happening at this level. And there are two examples here. One is the Skylake architecture, and there's ample opportunity shown here for both speculative exploits and timing channels to get that information back out of the microarchitecture. The one at the top right is one of my favorites. It's a way of using speculative forwarding of memory addresses as a way to access physical memory in an underlying server that isn't even mapped into your address space, right? That's kind of impressive. So what looking at this has led us to is a different way of thinking about abstraction in terms of a hierarchy of automata. One way to think about it is we're looking at it more the way somebody doing testing does than perhaps somebody that's doing languages, although I will freely admit to not being a language theorist, so I may have that wrong. But fundamentally, we're looking at this as a programming problem, based on a process model, or at least a model of processing. So you're programming the system at the top level. There's some internal state that's captured there. There's a correspondence between that and a controlled interface in the lower level system. So think ISA and CPU here. But there's an awful lot going on in that lower level system that's not directly controlled by what you're doing. And as I said on the previous slide, has really very little to do with maintaining the invariants or the guarantees that you've set at that level. For those that are familiar with, for example, Thomas Dillion's work, one way to think about this is it's a lot harder to identify what the weird state is in the concrete automaton. And again, ensuring that you've got a valid set of instructions at the ISA level doesn't help with this. One of the key characteristics of the models we're building is they have both metric and ordinal time explicitly represented. This slide shows both why and how, as well as some things about the modeling approach that we're taking. This is modeling Spectre 4, which is called a speculative store bypass. In 10 seconds, it means that you're allowing a read operation to jump in front of a write operation based on the assumption that the two address ranges don't overlap. If they don't, you're good, you keep going. If they do, then you have to roll it back. What matters here is how long that speculative window is, how long it is before the CPU, flags the fact that the addresses do in fact overlap, and B, when that execution actually gets rolled back. And those are not the same event. So one of the things you need to look at in terms of these architectures is, when do those processes happen, right? When is this exception flagged? And when does the CPU actually say, no, I have to roll all of this back? If it's right before these instructions are going to commit and then have a visible effect in the architecture, you've got that much longer to do whatever you're doing in this speculative window. There are two different variants of this, which is interesting because neither of the people describing both of them don't really talk each about the other. One of them is slow retrieval of information based on resolving an address in a register, and the other is that the store buffer itself can actually take a long time to decide whether or not two addresses alias one over the top of the other. Our approach all the way through this is to model this. What I meant by just enough details, we want to model this at a level where you can frame the question as, can you rule out that a given vulnerability, exploit, or class of exploits is possible within this particular architecture? The reason I frame it that way is because there's an awful lot of detail that goes into these, and we would very much like the designers to be the ones that have to present that argument, as opposed to having to dig all the way down into those details ourselves. In some cases, we can't get those details because they're proprietary. Now, the following slides have got some other concrete examples of the kinds of modeling structures that we're building. This one's actually part of the abstraction interface. What's going on here is you have a set of instructions, right? These are our ISA level instructions, in this case for the Ariane RISC-V architecture. And what the Ariane architecture, well, one, it guarantees that you will see the results of these in the same order that you believe they're being executed. The way the underlying CPU is doing that is they're dispatched into the execution engines in order. They're committed, meaning the results appear back in the, at the next level up in the abstraction at the architecture level in order. In between, you don't know how it's going to happen, right? I mean, this is at this level, you've got a flexible model that's representing something that's architecture specific. If I was doing this for the x86, it would be different and much, much messier, which is why this is a good example. But by composing the top 5 automata representing these instructions, and the two at the bottom that are enforcing this ordering, I actually have the basis for reasoning about what flexibility the CPU may have to reorder things in a way that can cause some interesting results without changing the semantics of what's seen at the architectural level. That part's important. One of the things that can force these orderings is that you have information dependencies between different operations. You could think of A1 and A3 on this slide as different microoperations that are passing a value one to the other. What this actually represents in the underlying architecture will depend on the architecture. You could think of this as the RION scoreboard. You could think of it as renamed registers within the x86 architecture. The point is that A1 is computing some value, which is V, which is then going to be stored in a register, which is R. Then the fact that that information is available is passed to A3, which then does something with it. And again, whether that's done using tags being passed within the x86 or it's being done in the RN scoreboard is something that we're agnostic about and would prefer to remain agnostic about. What matters to us is the dependency itself. A further example of this is what happens in terms of the memory hierarchy. And this is the first one that's really getting at the fact that all of that other space in the concrete architecture, the concrete automaton, is stuff that you don't control. So in this case, the top level is a micro operation that is storing a value, and then ultimately will commit the results of that micro operation. That's the commit in the top level line. The blue arrows represent synchronization, meaning that automata that otherwise are running asynchronously at these points have to be executing at the same time. So at the same time, these all kick off. The bottom one is affecting the store buffer. The middle one's affecting, in this, we've only modeled one level of cache. The top one's affecting main memory, and that's why it's got an additional synchronization point, because typically you're not going to allow that operation to commit, that instruction to commit back to the architectural level. I inverted that. You're not going to make the changes to memory until that has committed. Because if you end up rolling it back, you don't want that stuff to be visible at the architectural level. And if it's in memory, it is. If it's in cache or in the store buffer, it's not. The other thing we need to model here is speculation. Kiriansky et al. Has got these three different types of speculation, which we find to be a useful taxonomy. One is branch speculation. The CPU, either direct or indirect branches, the CPU decides which way it's going to jump. And so the speculation is just a single sequence of instructions, which may need to get rolled back to the point at which it guessed wrong. Exception speculation is something like a memory fault. Meltdown's one good example of that. Address speculation is something like the speculative store bypass in Spectre v4. There's a couple of different ways that this can be modeled that aren't always carefully separated. One of them is it's actually exception speculation. Foreshadow or riddle or cache out would be examples of this, where you have what are effectively aliased addresses, and it's the memory management machinery that eventually figures this out. Speculative store bypass, on the other hand, is happening locally in the CPU, and it's not a matter of there's an exception that interrupts what the CPU is processing. It's the CPU is caching the fact that it was going to speculatively decide that these two memory addresses do not overlap, and later finds out that they do. Last slide. Comments, conclusions. Yeah, what we're doing next. We've talked about this automata-based language. You've had, all of 3 minutes worth of introduction to it. I'm happy to talk more. There is a bit more detail in the paper. And then using the language, we've talked about these composable primitives, and I've showed a couple of examples of those. One thing I wanted to highlight here is, despite the fact that what I've talked about and what we've done on the Decimal project is really focused on speculative execution, that's not remotely a limitation of this, right? Anywhere that you're looking at this kind of an abstraction boundary, I think we've got a handle on it. And adjacent to what we're doing now is, for example, some of the work on weird circuits that I referred to previously, where you're using the microarchitectural components to define your own machine semantics. I would very much like to spend some more time poking at that one. As far as wrapping up on the current project, since our project and AIMEE as a whole are coming to a close, we're going to continue refining the types of primitives that I've showed you a couple of examples here. And then I think there's a lot of work to be done going on from this. in a couple of ways. Big one, or the one that I find most exciting is, what can you do with some other things? What can you do with um, weird circuits? What can you do with other forms of hierarchical composability? There are a lot of them out there. And I think I'm probably out of time, and that's my last slide.